Yeah, so as I was saying, assignment 2 is also available now. I know somebody reached out to me earlier while it was still in progress. So hopefully there are no mistakes, but if there are mistakes, please let me know so that I can help clarify and update this repository. So I would suggest, do keep a track of what's going on in terms of, the assignment document. In case you'll get an announcement from me or the TA in case something needs to be specified or clarified or changed. Okay, so there's a couple of questions, or basically 3 questions. One is about gradient descent. The second one is about doing classification using regression. And so we've been spending time on regression last session, and we'll spend some more time on it. Because the emphasis on this course, as I was mentioning in the first lecture as well as the previous few lectures, is not so much about covering a broad variety of models, but even with like one prototypical model class or one prototypical machine learning problem setup, really understand all the nuances that go into thinking through the design decisions, decisions about model class, decisions about what's happening, what's features and so on. So there's a lot of decisions to think about, or different aspects to think about while doing any ML work. So we'll try not to be like, we'll not try to, hopefully we'll try to spend enough time on each model, I guess. That's the point. So the second question is about regression. And so we'll see some more regression stuff today. And briefly, there is a small question on likelihood maximization, in general maximization. So most of these questions are for you to practice. Okay. The most important thing as a business analyst or the data scientist is the ability to write enough, code, or basically procedures to do statistical modeling or analysis or visualization, whatever it may be, right? So the hopefully the assignments help you exercise those muscles. Okay. Let me actually come back. So take a look at the assignment, when you can. It's due in a couple of weeks, so certainly have a look at it sooner than later. And if you have questions or if you spot some mistakes, please let us know. You can actually even let us know the mistakes directly by using the issues tab here if you want. I can show how to do that later on after the lecture, perhaps. So you can always drop email to us in case you find something incorrect there. Okay, so let's come back to where we were. So we are here. So it's just an exception for today that it's online. So in terms of the collection of models that we have looked at, we have seen k-nearest neighbors, we have seen decision trees, we have seen linear regression quite a bit, and we'll kind of wrap up today. And today we'll get started into thinking about, again, a statistical perspective, which is the notion of likelihood, maximizing the likelihood, and so on. And we'll look at logistic regression, which is also a linear model for the classification setting. And if time permits, we'll try to look at generalized linear models. Okay, so that's the agenda for today. So we'll continue with linear regression and hopefully cover a little bit ground on what is likelihood and what is maximum likelihood estimation, and also talk about logistic regression / generalized linear models. And if you have any questions, you can use the chat or unmute yourself and please ask. Okay. Yeah, there's some comment on the chat. Let's see. So the question is about, okay, this is a question about logistics. So does everybody in a group have to submit the assignments individually, or is one submission enough? One submission is enough. Okay. And but if you want to, so it's not optional in the sense that we do want one submission per group. Beyond that is definitely not necessary. But in terms of actually working through the assignment, if you really want to challenge yourself, I strongly encourage individual team members to try it out individually if you want to challenge yourself. Okay, so it's still feasible to do an assignment individually, but certainly you need to collate your efforts, discuss, and hopefully provide one solution. Okay. So I'm trying to find one of the previous slides just so that I can connect properly. Let's see. Okay, so in terms of, I'm directly showing lecture slide 02B, and that's because we were towards the end of lecture slide 02A, but you'll see that those last four slides have been covered and are also captured in this slide deck 02B. And so we'll look at 02B directly, okay? It's the same content, so we're not missing out anything from the previous slide deck, okay? 02A. So let's start with yeah. So let's start with this slide deck 02B. Okay, so let's see. So I'll do this. I'll make it a full screen. So just let me know if you're not able to see the full screen version, but you're still seeing the tabs and navbar and so on. So I full screened it. So if you're not able to see the full screen, just let me know.
We can see it on full screen, Professor.
Okay, that's great. So yeah. So if you recall from last time, let's recall the illustrative data set. So the illustrative data set had, let's say, a couple of features. I think last time we even talked about 3 features, 4 features, and so on. So let's say, for simplicity, again, back to some common illustrative example. Let's say there are 2 features, homework and exams. And let's say we have a numeric output variable, which is score. Okay, so the table looks like this. And we want to predict score given these 2 features. Okay, so this is actually just an illustrative plot. This is not realistic because we have kind of condensed 2 of the features into the x-axis, homework and exam scores. But this is for just the simplicity of illustration. Ideally, if there were 2 features and you had an output variable, you would do what is a 3D plot. You would plot a 3D plot. Okay. So you can see as a function of the features, you have score, which may have a pattern like this. It's these colors just indicate some thresholding of the scores. For example, scores greater than let's say 90 are blue, scores between 90 and 80 are green, and so on. Okay, but you have a pattern like this of where the scores are. So y-axis represents scores. So some higher the values, scores are higher. So, and at test time, you've given a new data point, right? Let's say this black data point, and a linear model or any model would, at least in the regression case, would try to fit score as a function of these input features, right? Remember the hypothesis function, such that it can say something about this black dot. And rather than using complex models, so complex model is illustrated here by a wiggly red line. Instead of that, we're going to stick with a linear model. Okay, and we'll talk about why linear model. So linear model is in a sense more biased, in the sense that we are searching for simpler functions. So we are biased in the sense that we are imposing a preference that we want a simpler model, which is according to the specification that we talked about last time, which is that h theta is a bunch of theta coordinates times x coordinates, element-wise multiplication, add them up, and that's my model, right? So So this is an example of a simpler model, which is a linear model. So a linear model in this illustration should look like a line. Okay, if you have a yeah, so score should look like a line as a function of the input features in this illustration. But if you had, for example, a two features, which is actually we do have two features, then the two features would span an XY space, and then the score would be like a surface. Okay, so a plane in 2 dimensions. Okay, so this is a linear model. A complex model is just, for illustration's sake, we are just plotting it like this. It's a, just to think of a polynomial, let's say of high order, then it can go up and down. Okay, like a third order polynomial, or instead of a quadratic function, think of a function which is x to the power 3 plus some x squared plus x cube x plus y, plus constant. So a polynomial function can wiggle around. Okay, so higher the degree of the polynomial, there's more flexibility to go up and down. But we were, last time we did not even talk about functions beyond linear, so we were really focusing on linear models. But you could imagine that functions which map from features to output could be non-linear, as in beyond linear. Okay, and one of the, I guess, popular functions in that non-linear category include deep neural networks, or in general neural networks. Okay, so let's really stick to linear hypothesis, because there's still some questions we wanted to answer with respect to estimating theta. Okay, and that perspective that we're going to take today is going to be linear algebraic, and then we'll also talk about some statistical perspective later on. Okay, so remember, if you remember, h theta of x is our hypothesis function, or the template, or the specification of which type of function that we want to estimate the parameters of, and the parameters are represented by this Greek letter theta, which is actually theta 0, theta 1, and theta 2 together. So you can think of that theta as a vector with theta 0, theta 1, theta 2 if you want. So the specification of the function looks like this. So it's just a product between feature coordinates, and then sum theta 1 times x homework plus theta 2 times x exam, and add an offset theta naught, and then that's your prediction for the score. Okay, so in that sense, so for the black dot, you can get some estimated score. Okay, which is as long as which is what the linear fit suggests. Okay, so the dotted line suggests, okay, if the black dot lies here on the x-axis, then the y-axis, you can read off the y coordinate there and suggest that that's the score for Diane. Okay, so in real life, data is going to be extremely not linear. It's very rare that things are going to be linear. Still, linear model is a very good model to start with. So here's an example where you can see that if you plot, for example, let's say you're trying to predict, there's a coordinate called total page. So don't focus so much on the particular data set here. We will be working on a specific data set in our assignment number 2. And so there you'll get a chance to make such plots. So here we are just looking at total miles driven. So it's related to automobile data set here. Total mile driven versus total paid. And you can see that the relationship, is not exactly linear, but you can actually make a approximation that perhaps it is linear and fit a linear curve, okay, relating the y variable here, the y-axis variable, to the x-axis variable. Now, how good is the fit? As you can visually see here, it doesn't seem like such a good fit, but so in real life, it's always this trade-off of choosing more complex models, complex fits, but then they may be overfitting to the data, versus something simpler like linear models, which may not be fitting to the data well also. Okay, so there's pros and cons with whatever choice you make. And so there is some, so that's why it's not a formulaic, I guess, process to apply machine learning in a particular domain. Okay, but so in real life, linear models may fit or may not fit. But let's say, it is a good model class, and so let's study it further. Okay, in particular, we're going to focus on how to pick the parameter theta, and we'll And so for us, the setting the estimation problem becomes, given this data set D with xi by I, where xi belongs to, so this inverted symbol is belongs to the n-dimensional vector space, and yi belongs to the one-dimensional vector space, or just the real numbers. How to pick the best parameters? Okay, so theta here, we're just using theta hat, kind of symbolizing that it's an estimated quantity. Okay, but we'll see this hat or some extra symbol on top of the theta in later slides. Okay, so I think last time we spent quite a bit of time trying to say, okay, even if you have the data set, you want to estimate theta, first you need to say how do you want to quantify one theta is better than the other, right? So for that, we defined a performance score using basically a loss function. Okay, so the loss function is basically trying to say how close, given theta, you're able to make all sorts of predictions. So let's make predictions on the training data itself, on the data set itself. So if I make my predicted scores, if I produce predicted scores given a theta, then they'll be either close or not close to yi's. And if they're close to yi's, maybe that theta is good. If they're not close to yi's, maybe that theta is bad. Okay. Okay, so last time we saw this squared loss function, which is which if for a generic point x comma y, the loss function was just defined like this: 1/2 times h theta of x minus y, the whole square. Okay, where h theta, again, if you remember, is just element-wise multiplication, coordinate-wise multiplication. Like coordinate of feature vector times coordinate of the theta parameter vector, and then sum each of these element-wise products together and add theta naught. Or basically you can think of one of the features coordinates to be x naught, and that is equal to 1. And so then this whole thing, you don't have to have a special case for the intercept. Okay. Yeah, so the cost for the full data set D would be just a sum over these scores or loss per each example. So the first line was showing the loss for a generic data point, okay, single data point. And so you have little m number of data points, for example, the 100 data points, okay. Then you will sum over 100 of these such terms. Last time somebody mentioned, hey, we could also do normalization, which is that you can define j theta to be equal to 1/2. 1/2 is just a constant, but you can also add another constant, which depends on the number of examples. So you can have in front of j theta, or while defining j theta, you can say 1 by m. Okay, m is the number of data points, like 1 by 100. Okay, so that would just show it as an average instead of a sum. Okay. Now the last line is just a recap for many of you. Is an expression to. It is just again a shorthand to say something that we say in English, which is theta hat. We want to find theta hat, which is the argument is the argmin, which is basically the is that theta which minimizes j theta function. Okay, so it's the argument of the minimum of j theta that you can achieve in the domain of theta that we are searching for, which is just the vector space. Okay. Last time somebody had a comment, but what if we're searching for theta in a restricted space? Like, hey, I only want these thetas, like theta naught or theta 1 or theta 2, all the way to theta n, let's say. They only have to be between 0 to 1, or let's say 0 to 10 units. Okay, maybe there's some reason why you want to impose that preference. Okay, so that preference, again, you would just, in the shorthand notation, you would explicitly mention that, hey, theta belongs to the set that I want to search over. Okay, it's a set, right? So even a vector space is a set. It just has extra properties, but it's a set. It's a collection of elements, right? Vectors. So you can explicitly say that in the shorthand notation as well. So theta belongs to a set over which I'm searching over. So it's a search problem, searching for the theta. And for every theta, you have a score, right? Overall score. And the score, of course, involves the data set. So you can find the theta which corresponds to the lowest score, in a sense, because score is the sense of a loss. So lower is better. Yeah, and last time we spent a considerable amount of time talking about a numeric procedure to find a candidate good theta, and sometimes even the best theta. Okay, so basically, as the slide says, we want to choose the best theta or theta hat that minimizes this cost j theta. Okay, and so the gradient descent algorithm template was that you start from a random initial point and you keep making some progress towards keep making progress in the sense that you start with a random initial theta candidate, and then you're gonna start an iterative loop where in each iteration you're gonna improve on the theta candidate. So you'll have some starting point, let's call it theta old. By one step of the iteration, you'll get a theta new. And how do you go from theta old to theta new? You're gonna use gradient information. Okay. And then in the next iterate, the new thing that you computed is going to be the new is going to be the theta old for the next iteration. And then again, you're going to make a gradient step and get to theta new and so on. Okay, so repeat until you're satisfied. So either you can have a for loop where you can, hey, I only want to run 100 iterations or 1,000 iterations, or you can do a while loop where you check for a terminating condition that, hey, these thetas are not changing too much. So maybe I have minimized the loss that you cannot further, probably you cannot minimize loss further. And why is that? There's a property for the loss function. One of the desirable properties for loss function is that one of the desirable properties that you would like to impose is that the loss function doesn't go below 0. Okay, so you can keep iterating over theta, and you know that loss function cannot go below 0. So at some point, if either you make progress, maybe you go all the way to 0, and after that you will, you don't need to, continue further, or you may make progress on theta such that loss will always be some fixed value, let's say 0.1, and it never decreases less than 0.1, let's say. So there is a way to stop. Okay. And we saw last time we had this brief discussion about convex or nice looking loss functions, which is the case for squared loss and linear models. Or you could have a nonlinear loss function, which is the case for example, the same squared loss, but a nonlinear function such as a neural network or like a deep neural network. Okay, so but we are not talking about nonlinear stuff. So here's an illustration. If your parameter theta was linear, was one-dimensional, then this is an example plot. Okay, in fact, you can do this type of plot. Maybe there's a subpart in your assignment which asks you to do this, but basically you can in one dimension. Let's say your j theta is a function of one parameter that you want to optimize. Theta is only one-dimensional, so one number. Then theta, you can plot theta on the x-axis, and you can actually plot your complete loss function. Okay, you can evaluate theta at every given point. Let's say you make a grid. Okay, theta is equal to 0, theta is equal to 0.1, theta is equal to 0.2. You can evaluate the loss, and you can, if you plot it, maybe it look like a ball. Okay, so this is just an illustration. So it will look like this parabola here, y is equal to x squared. And then you start with some initial value, as you can see in this illustration, some blue dot towards the far left. And then your iteration, each step of the iteration, you're going from one blue dot to the other. Okay, so you can see that you're going from one blue dot to the other. Once you come to the bottom of this loss function, which is around this yellow point, you'll see that there's not much change from theta old to theta new. Okay, if you take a gradient step, you're not going to change much. And why is that? Because you can see that the gradient at the bottom is actually 0. Okay, how do you know? So what is recall what's the gradient? In one dimension, gradient is the same as, partial derivative is the same as the derivative. Okay, so if you look at the bottom, if you say, hey, if I slightly change from, let's say, the yellow point to some positive, some point slightly right to it, okay, you can see that the loss function, or in this case cost, doesn't change much. In fact, it doesn't change at all. Okay, so that's why the gradient at the bottom is 0. And so since the gradient at the bottom is 0, theta old is going to be theta new. Okay, so is any questions here? It's just a recap of what we discussed last time. Okay, so here's a different figure. It's just increasing the number of, it's increasing the search space from 1 dimension to 2 dimensions. So here, instead of plotting cost as a function of the search space, which is the x-axis here. So here, both the x-axis and the y-axis is together from the search plane. Okay, so theta naught and theta 1. This is the case, for example, if you're doing simple regression where you only have one feature and one output variable. Let's say in that case, what you can see is from the top view. It's like, for example, if you've seen Google Maps and so on, you can get what is called a contour plot. Okay, so this concentric circles, it's not exactly circles, so concentric curves are at the same elevation level. Okay, so this is actually the top view of a ball. Just think of the innermost circle, like the smallest circle here is like the bottom bunch of points on the ball, which evaluate to the same level. Okay, and similarly, the next circle after that is on the ball, some bunch of points which evaluate to the same value but a little bit higher, and so on. So all these circles basically are like the top view of this ball, where the connected points are just points which evaluate to the same cost value. Okay. So this is the type of plots you would see, for example, such contour plots you would see, for example, if you've gone hiking, on mountains and so on. So you can see that the starting point here, it's represented x naught, but you can just think of this some first value of theta vector, which is two-dimensional here now. And then you can actually see the gradient. Okay, so this red line here is actually the gradient direction. Okay, it's actually the gradient itself. And you can remember you would typically scale the gradient with some learning rate or whatever step size, and you go in the opposite direction of the gradient. Okay, so if you think of the actual gradient at x naught, it's a vector which is going which is directed outside. Okay, so which is going the opposite way. But if you take the negative of it, it's going to go towards the center. And this magnitude of how much to go from x naught to x1 is also determined by that step size. Okay, we'll see that formula in a second, but this is the intuition. Okay, so you can draw the gradient because we are looking at the 2D plane over which we're searching. Okay, and you can see you're making progress, and hopefully you'll get to the bottom of the ball or close enough to it. Okay. And the same figure that you saw in this slide, you can visualize this in a 3D plot, and that concentric circle is exactly like basically if you slice this curve with that you're seeing in 3D horizontally, slice them, so you'll get those concentric circles. Okay, so for linear model specification and square laws, we already discussed last time that the cost function happens to be convex. Okay, we'll not look at the definition of convex right now. Maybe later on, one of the later slides when we're talking about support vector machines, we'll probably come back to convexity. But right for us right now, convexity just means that there is only one bottom or one minima point, okay, of this function. So the function doesn't have wiggles. It either goes up or goes down. So there's this one valley basically. Okay, and that's what you can see here. So the star at the bottom of this blue area is kind of representing, hey, that's the bottom of the valley. Maybe that's the optimal. That's the minimizing theta, vector, theta naught, theta 1, if you vectorize it. Okay, and here's the illustration from last time as well, which is a function in 2 dimensions, which is which has multiple valleys and hills. And so if you start from some point, you may get to one minima, or if you start from a slightly different point, maybe you get to a different minima. So okay, this is something that is a consequence of not just a loss function. Okay, so the loss function could still be squared loss, but if the model which maps from if the model is not linear, okay, so for example, a neural network model would have a loss function like this. Okay, so in terms of its parameter space. But if it's a linear model, then you will not have a surface like this. You can get a surface like this even with linear model if you come up with a very non-standard loss function. Okay, so this convexity is a result of either you specifying a linear model and some very crazy loss function, or you pick a nonlinear model and still keep the loss function to be like a squared loss. Okay, so you can change either the loss function or the model specification itself to kind of get into harder situations like this. And last time we saw for a single training example how the gradient look like. Theta j nu So it just means that there is a left-hand side is a new one, right-hand side is the old stuff. And so this is not exactly equality. I mean, this is just like assignment operation. So the new stuff, which is the left-hand side, is going to be updated using the old information. So like older theta j, according to this update rule. And so this was theta j. So j is the coordinate, subscript j is like the coordinate. So in the previous slide, theta naught and theta 1, there are two thetas. So theta naught and theta 1 would be the true 0 and 1 would be the two values for j. And it's learning rate times gradient of the loss j divide gradient of the loss, but only at theta j. So basically, this is the partial derivative of the loss function with respect to theta j. Okay, it's just called a learning rule, which was studied earlier, but it's basically an example of gradient descent. Okay, so if you have all examples, the only thing that changes in the bottom equation is a summation over all the examples. Okay. And we saw this is exactly how it works for the squared loss. Okay, because of the 1/2 in the front and square operation, if you take gradient, this is exactly what evaluates to. Okay, so stepping away from the choice of a linear model for a second, this expression here in this slide is showing the gradient descent procedure or the algorithm. By the way, procedure, algorithm is the same thing. So don't worry too much if somebody says an algorithm. It's just a procedure, which just means a sequence of steps. Okay, so the gradient descent procedure, when your loss function is a squared loss, okay, and your model choice is a linear model, like h theta is linear, is like this. Okay, so of course, if you have a slightly different loss, let's say to the power 4, then you will have a different gradient. Okay, so gradient descent or batch gradient descent is saying, hey, think of it, there's iterations as epochs. In each epoch, what you do is for each coordinate of theta. So let's say if theta is only 2-dimensional, then this internal for loop is for two times. If the theta is let's say 3-dimensional, then internal for loop runs 3 dimensions. So it's doing coordinate by coordinate of theta, of the theta vector. Okay, it's just saying, hey, the new theta is the old theta minus some again a scalar value which depends on the data set. Okay, so x superscript I and y superscript I data, and h theta is the current values of or the old values of theta, okay, which determine h theta of x. So this is what is the gradient descent procedure. And so we have discussed this at length, so we're gonna not spend too much time on this today. But last time we saw actually a couple of variations, so I want to briefly mention them as well. So for each epoch, we are actually, so for each update of theta j, so each coordinate of theta when we're updating, we're actually looking at all the data set. Okay, so all the m examples are being considered when you're updating each coordinate, right? So it's there is some trick to not look at all the coordinates of the data set while doing the theta j update. Of course, now then that would not exactly be the gradient of the loss function, but it's just a proxy for that. Okay, so we can do that, and that's given by stochastic gradient descent. So what changes is this: we still have that for loop over the coordinates of theta, but instead of doing an update which involves all the examples at the same time, we do an update. For example, we do once per example. So there is an outer for loop in this version of stochastic gradient descent. We have an outer for loop where we are picking an example. Given that example, we are updating all the coordinates of theta. Then we're going to the next example and updating all coordinates of theta, and so on. So computationally, there's a lot more updates on theta going on here compared to the previous for loop, right? So previous for loop, each coordinate, look at all the data and do one update. Here it's like for each example, do an update on the theta vector, and again pick the next example, do an update on theta vector, and so on. A lot more updates. So of course the updates are not going to match. So one version may be better suited compared to the other, depending on the context. But there is a reason why this version was kind of proposed. It's because when you look at the theta update, it's not at least looking at all the data. Okay, and that elevates the concern. For example, if you have millions of data points, then one theta update, you don't need to worry about summing over all the million terms in that gradient expression. Okay, of course you may say, hey, there's still a for loop over million data points here. So what folks do is generally they may not, they may maybe only pick a subsample out of the million observations for this step. Okay, but for now, let's just stick with what's written here. This is a version of gradient descent compared to batch gradient descent. Variation is that there is no summation over h theta. Sorry, there's no summation over the examples here. So there's a question which is, in what scenario stochastic is chosen over batch? So you will see that in practice. So in practice, if you're really building all this from scratch, essentially, then your choice of stochastic versus batch really depends on whether you need, whether you're handling a large data set or not. Okay. It turns out, and this is more of a, people knew it before, but it's more kind of become is further being looked into these days, is the impact of the algorithm while determining the solution. Okay, so if you just look at this, right? So irrespective of whether I use batch gradient descent or stochastic gradient descent, at the end of the day, I just want this bottom, right? The thing at the bottom of this this loss function, and both of them do get there. Maybe some slightly different computational effort needed in practice, but the way we've written the algorithm procedures, they take equal amount of additions and multiplications and so on, the way we've written in the slides, the next two. But for example, if you think of, let's say, training deep neural networks, the method of choice happens to be stochastic gradient descent. Okay, and that's because when you train deep neural networks, you really work with millions of examples, and so you do want to be not doing that summation. Okay, so you can't really average out gradients across all the data at the same time. Okay, so that's something, and so the community has converged towards using stochastic gradient descent and its variations, not just stochastic gradient descent, but there are other approaches very similar to it. They are the ones used for neural networks these days. Okay, but in theory, both have pros and cons, and there's no reason to eliminate one. Okay, completely. Yeah, so it says, as a point stays in the slide, you may get faster convergence, you may get to the bottom quickly, but since you're only using one data point to kind of approximate your gradient, it could be completely off. Basically, the right gradient is actually shown here. So this is the gradient of the loss, which is the right thing. If you ignore statistics, if you just think of search problem, this is exactly the gradient of the loss, and so this is the right thing to do. But you could, use a proxy like this, which is a gradient only on a small subset of data. In fact, just on one example. And because of that, your convergence, like the way you're iterating over may be like quite wiggly, okay, quite shaky. If you think of this type of plot, yeah. So instead of going directly going, maybe approaching all the way to the bottom of the ball, you may be like going like you may doing zigzag stuff, okay, zigzag stuff. Sorry. Okay. So, and there was a version in between, which is called minimatch gradient descent, where instead of looking at, so in the outer loop, so what changed is instead of just looking at one example or all examples, you look at, let's say, 10 examples at a time. Okay, it's in between. It's kind of interpolating between stochastic gradient descent and batch gradient descent. So you take 10 examples at a time and do a gradient update. So and do an update on your theta coordinates. Okay, so you can try all these, and you will have an opportunity to do so in the assignment. Okay, so that was a review of what we covered last time. So now I want to spend a little bit of time on a different approach to, at least for the linear model case and the regression setting, a different approach to get to an estimate. Okay, get to an estimate of the parameters of the model, which are thetas. Okay. So again, this is just a shorthand, by the way, as I keep saying throughout the previous lectures and this lecture, you don't have to memorize the shorthands or use them fluently. Okay, that's not the purpose. But the purpose is to be more professional, a little bit more, formal in the way you're stating things, as when you're communicating with other data scientists and business analysts, or even sometimes the stakeholders, to be a little bit more precise. Okay, so with that, the way we read it in English is also something that you could write. Okay, so you don't have to use this notation here. So capital X here, it just represents the matrix, M cross N matrix. It's the input data matrix, and little y here represents the m-dimensional vector of scores or outputs. Okay, scores, I was saying the illustration we had scores, but in general y represents the output values. Okay, so little m is the number of observations, and n is the dimensionality of n is the dimensionality of features, or n minus 1 is the dimensionality of features. As you can see here below, little n is 3 and m is 5, so we have five rows, and number of features is 3, but we tack on one more kind of degenerate feature so that we can represent the whole thing as a matrix vector multiplication. So that feature is here, so all ones feature, and then x1 feature, x2 feature, and x3 feature, and that times theta vector. And now, since there are 3 features plus 1 intercept, and so theta naught, theta 1, theta 2, theta 3. So they, hopefully, since we are making a linear model, each row, our prediction is exactly a row times this column. So that hopefully is close to y's for that example. Okay, so that's represented with this. So x times theta hopefully is close to y. Because that's what we mean by finding the best theta. So we want theta such that the left-hand side computation matrix vector multiplication produces a m-dimensional vector which is as close, ideally equal, to y as possible. Okay, so that's the sense. That's exactly the sense that was also captured in the loss function, but just wanted to kind of mention it here. Yeah, so that notation. So the squiggly equality just means that it's again an informal notation. It's actually, you don't have to write it this way. It's just saying x times theta, we want it to be as close, approximately close to that little y vector. Okay, let's say which is 100 dimensional. So sorry, in this example, it's 5 dimensional. Okay, so let's now try to understand what property would this best theta satisfy. So for that, let's define another vector. Okay, it's going to be an interesting vector, and you might have seen it before in other treatments of least squares, as well as you'll work with residuals in the assignment as well. So we'll define the residual vector R to be, it depends on theta. So if you pick a different theta, you'll get different residuals. So residual vector is the same length as the y vector. Okay, so if you have 5 examples, residual is a 5-dimensional vector, y is a 5-dimensional vector, and x theta is also going to be 5-dimensional vector. So residual is a 5-dimensional vector, let's say. Okay, same dimensionality as y. Okay, now the search problem. Okay, the search problem is stated in a slightly different way, which is finding a theta that minimizes the 2 norm square of the residuals. Okay, so think of the R vector, which is defined in the first bullet point. The perpendicular lines subscript 2, superscript 2 just exactly are defined as shown in the sub point here. So the perpendicular lines subscript 2 for any vector is just the magnitude of that vector. Okay, so the Euclidean magnitude of that vector. Okay, so which is just the square root of r1 square plus r2 square plus all the way to rm square. So why is it r subscript m? As I said, r is a vector which is the same length as the number of examples. Okay, and the whole square. So you kind of remove the square. So this if you have connected the dots, this is exactly the loss function that we saw a few slides ago, j theta, except there's no extra 1/2 in the front. So if you added 1/2 in the front of r, so this 2 norm square as 1/2 times 2 norm square, then it will be exactly the same as the j theta that we saw earlier. Okay, so we want to find theta that minimizes this residual. Okay, so why do you want to minimize the residual? Remember, our objective is to find x theta as close to y as possible. If it is exactly equal to 0, then residuals is equal to 0. Okay, so smaller the residuals, the better the theta is. Okay, so because we want left hand side to be as close to y as close to the right hand side in the system of linear equations. Okay. So and just to be verbose, I mean, like really detailed about it. So r is equal to y minus x theta is exactly this. So y minus x theta is just theta naught times 1 plus theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3 in our running example. So 5 rows, and each entry in R is exactly defined this way. Okay, so it's element-wise products, and that's the definition of H here, H theta, and y1 is the first example's value, okay, output value. Okay, so that's the short form. This is equivalent to what we saw in the previous slide. And as I said, R2 square or 2 norm square is exactly equal to j theta, except for a factor of 1/2. So either you multiply 1/2 to 2 norm square of R, or you multiply 2 with j theta, so that they both are the same. Okay. So the argmin, so in this slide, I guess the goal of the slide is just say that theta hat, let's say, is the argmin of the loss function, which we talked about numerically getting to it using gradient descent procedures, the same as minimizing this residual vector 2 norm square. Okay, but we'll try to get to, try to think about how to get to this minimization of the residuals 2 norm square without using gradient descent, without using gradient descent approach, but a slightly different idea. Okay, and that is, I guess here we're calling it finding theta hat analytically. Analytically just means getting a formula. Okay, so given the data, can you give me a formula for theta hat? Don't tell, if the formula is different from, I guess, a procedure or an algorithm. So given data, I can tell you a procedure, which is, let's say, gradient descent procedure to get to theta hat, or this best model. Instead of that, given the data, give me a formula which can directly give me theta hat. Okay, so formula in our case, it essentially just means, hey, if I can represent data as a bunch of vectors or matrices, can you tell me theta hat, which is a vector, in terms of these vectors or matrices? Okay, and we'll see that in a second. And for that, we want to introduce the following idea. Let's say R of X is the range space of X. Okay, range space just means, hey, X is a matrix. Multiply it with any appropriate sized vector, it's going to produce another vector, right? So collect all these vectors that it produced. Okay, so it's the range. Okay, all the vectors that it produced, and that set of vectors is called the range space of X. Okay, it's called the range space of X. Now, so in the bottom of the slide, we are showing the range space of X as a gray area. By the way, it's not restricted to be like this gray region. I mean, it will span, like if it's a plane, it will span the full, it's gonna go all the way to infinity and in each direction. But let's say for simplicity that this is the range space. Let's say, and there is a 0 in that range space, because remember, if I multiply X with all zeros, then it produces a 0, right? So there's a 0 vector in this range space. Now, you can see that if I multiply X with any, let's say, a theta, then you will have a vector which looks like this, X theta. So X theta is this vector going from 0 to some point. Okay, so it's a vector that lies in the range space, because we said, hey, the range space is the set of all things that you can get from multiplying X with something. So as I multiply X with theta, I got a vector, okay, like this, which lies in the range space. So this range space, remember, this range space is vectors of dimension m. Okay, so in our running example, m is 5, which means this is a 5-dimensional vector space. So X theta is a 5-dimensional vector. Okay, 5-dimensional vector. Similarly, Y is a 5-dimensional vector, but Y need not belong to the range space of X. Okay, so if it belongs to the range space of X, that's great, and which means that there is some theta for which X theta is exactly equal to Y. Okay, but let's say that's not the case. So let's say Y is not in the range space of X, then theta hat. So here's an interesting result. Then the theta hat, which is that argmin of the residual norm square, is that theta for which this residual, which makes r theta, r theta, so which is the residual vector, perpendicular to the range space. Okay, so the theta that minimizes the 2 norm square of our residuals, right, it's that theta such that the residual vector is perpendicular, is orthogonal to the range space. Okay, so y is outside this gray plane. There is some theta for which there is some x theta. It should be such that x theta plus this perpendicular residual together form the y. Okay, we know that r is exactly equal to y minus x theta. So what we're trying to say is that this r will be perpendicular to the range space. Okay, that's the best theta. So it's not. So there could be other thetas for which there is other thetas also lead to some different residual vectors, but those residual vectors need not be perpendicular to the range space. Okay, so that's the key result that that's a key property, and that will also lead to a formula in a second. But this is a key property that's new. We did not consider this when we're talking about gradient descent. Okay, but this is specific to our setting, which is linear models and square laws. So let's say we found a theta for which theta hat, let's say, for which that theta has such that r of theta hat is perpendicular to the range space. Okay, let's say that is true. What we're going to show is that for any other theta, its residual norm 2 norm square is going to be higher. Okay, so what we're going to show is, hey, let's say there's a theta for which let's say we found a theta for which the residual vector is perpendicular to the range space. For any other theta vector, it's going to be worse in the sense that it's not going to be perpendicular, first of all, and the performance, which is quantified by the residual 2 norm square, it's going to be higher. Okay, so apologies for the spelling mistake here. So think of this as plane, plane. So if a vector is normal to the plane, the vector is perpendicular to any vector in the plane. Okay, so that's what it means. So normal equations here kind of allude to the fact that a vector is normal to a plane if it's perpendicular to all vectors. Perpendicular just means the inner product is 0. Okay, and we'll look at that in fact in the next slide. So let's say we have a theta hat for which the residual vector is perpendicular to the range space. Okay, remember residual vector is m-dimensional, x theta is m-dimensional, and y is also m-dimensional. Okay, so let's say so let's say the r theta hat is perpendicular to the range space. Then what does it mean? Then for every z, okay, the z is not in the range space or anything like that. The z is something that we want to multiply x with. Okay, so for every z, okay, which is the same dimensionality as the theta vector itself, like let's say 4-dimensional, theta naught, theta 1, theta 2, theta 3, z is going to be similar for every z. So xz is something which is in the range space. Okay, so the normality just means that, or perpendicular property just means that xz transpose the residual. So this is the residual. R hat is nothing but y minus x theta hat. Okay, that's the residual. Xz transpose times the residual is equal to 0. Okay, they're perpendicular. Okay, if they're perpendicular to each other, their inner product is 0. Okay, that's just the definition. Okay, so that means so if you just expand, if you do a multiplication of a vector with another vector inner product here, you can use the properties of, hey, what is xz the whole transpose? Xz the whole transpose. Again, you have to look at the properties of transpose operations. You will see that it is equal to z transpose x transpose. Okay, so z transpose times x transpose, and then you can say, hey, x transpose I'm going to multiply with y. I'm also going to multiply with the inner term x theta hat as well. So x transpose is getting multiplied with y. X transpose is getting multiplied with x theta hat. Okay, this is the just a reduction from identifying that, hey, if r hat is perpendicular, then for any z, this equation is true. Okay, this 0 is equal to z transpose x transpose y minus x transpose x the whole times theta hat. Okay, this is just the equation that should hold. Okay, so since this 0 is equal to the right hand side should hold for any z, okay, for any z, right? I can pick a z which is not 0, right, and not 0 coordinate wise, right? So for any z this should be true. I pick a z which is not 0 coordinate wise, which means that the only way z transpose some, this thing in the bracket can be 0 is that the thing in the bracket has to be 0 coordinate wise. So if you have two vectors, right, two vectors, one of them is has some non-zero numbers, let's say in that, let's say that's z, is getting getting an inner product with another vector that should be equal to 0. That means that this other vector should all be 0. Okay, should element wise be 0. Otherwise, you cannot get a 0. Okay. So which means that this thing in the bracket is equal to 0 itself. Okay, is equal to 0 element wise, as in this thing in the bracket is a vector. Each coordinate of the vector should be equal to 0. Okay, so if the thing in the bracket is equal to 0, then the thing in the bracket is equal to 0. You can write it as that thing is equal to 0, which means that the second term is equal to the first term. So x transpose x times theta is equal to x transpose y. Okay, so this is the equation that some of you might have seen from some other class. This is the normal equation. Okay, so x transpose, okay, is the transpose of the data matrix. Okay, so the feature matrix, you take a transpose, multiply it with the data matrix. Okay, so you get a resultant matrix here. That times theta should be equal to data matrix transpose times y. Okay, so this is what theta hat, theta hat, which is a hat that makes that is perpendicular, satisfies. Okay, it satisfies the normal equation. Any questions here before I move forward? Okay, so let's actually so what we have done so far is we have kind of already come to a candidate formula for how to get theta. Okay, so we said, hey, 2 norm square of the residual vector is the same as the loss function from before that we saw a couple of slides ago. Then we said, hey, which theta minimizes this 2 norm square? Here's the candidate. Is the theta for which the residual is perpendicular to the range space of x. Okay, it's the theta that creates the residual vector, which is perpendicular to the range space of x. Okay, so what is the theta? The theta can be characterized by this equation. Okay, so the theta which makes the residual perpendicular to the range space of x is the theta that satisfies this system of equations. Okay, so we have gotten a candidate that from which we can compute theta. This is a system of linear equations. Okay, so you can solve the system of linear equations. If you remember from some earlier class, if you have a system of 3 equations, 3 unknowns, that's how this will look like. So it's like some matrix times some unknown is equal to some other known quantity. Okay, so it's a system of equations. You can always solve it either using pen and paper or through computational methods. You can use NumPy, or you can actually take the inverse. So it's something like theta is equal to this inverse of this thing times the right hand side, right? So we have a theta. We know it satisfies some property because of which we got a system of equations. Now you want to say, hey, why is that theta the one which minimizes the 2 norm square of the residual? Okay, let's briefly answer that. Okay, and the way we're going to answer it is by showing that, hey, if there is any other theta that's going to have a higher residual. Okay, so that's the way we're going to answer why is that the theta that we talked about, the theta that makes the residual perpendicular to the range space, is the one that minimizes the this function, this objective here. Okay. So let's start with theta hat. Let's say it does make a residual which is perpendicular to the range space. Now what we'll say is, hey, any other theta, it's going to produce a bad residual vector, in the sense that that residual vector will not have will kind of blow up this number here. Okay, the objective. So let's pick again any z such that xz is perpendicular to r hat. Okay, so we know there's so theta hat produces an r hat, right? That r hat or r theta hat is perpendicular to range space. Let's say that is true. Now what we're going to do is, let's say that, we'll say, hey, take any z such that xz is also perpendicular to r hat. We know that r hat is perpendicular to range space, so there must be some z for which xz is perpendicular to r hat, right? So that xz lies in the range space, and that's why it's perpendicular to r hat, right? So let's say that's xz here. Okay, it's in the range space. Now, if you think of, and this is for any z, okay, so any conceivable z which is not zero, okay, so for any z, then let's look at the how, because z, we have a z, then I can just say, hey, theta hat plus z, let's say that's any other potential theta, right? So any other potential theta candidate, right? So now let's look at what the residual for this any other potential theta candidate which is not theta hat is. Okay, so it's y minus x times theta hat plus z, right? 2 norm square. Okay, so let's look at this residual. So this is a residual of a different theta. Okay, the different theta is just theta hat plus z. Okay, so this residual square is just, if you take y minus x theta hat, that's exactly r hat, right? So that's r hat minus x times z, minus x times z. Okay, now r hat minus x times z, the whole square, okay, this 2 norm square, it turns out that is exactly equal to r hat square plus xz the whole square. Okay, so why is that? Remember, xz is in the gray space, is in the range space, and r hat is outside the range space. Okay, so you have vectors which are perpendicular, two vectors which are perpendicular to each other. Okay, that means their difference, or basically sum of squares, is just the magnitude of one vector plus the magnitude of the other vector. Okay, and so that's the magnitude of the first vector plus the magnitude of the second vector. So you can see that any other theta that I pick, I get the original residual square plus some extra quantity, which is always positive. So the last thing is always positive. Okay, so xz 2 norm square, we saw the definition, right? It's the sum of squares of the entries, right? So it is going to be positive. So any other theta that I pick other than the one which is perpendicular, it's always going to be higher because there's an extra positive term, non-negative term. And so the lowest you can go is when you are actually perpendicular. Okay, so that's why that's the theta that minimizes the 2 norm square. So any questions about this? Yeah, one extra technical point I kind of did not mention is that we are going to assume that the features are not redundant, in the sense the features are linearly independent. Okay, so but that's just that's something that's just needed to kind of say that the range space is not smaller than the it's not smaller. Okay. But otherwise, the idea is that, hey, any other vector that you pick other than the theta that makes the residual perpendicular to the range space, that vector will have a higher overall sum of square, it's a higher overall objective value. Okay. So what we've done in this slide, so here we got a candidate theta. We said, hey, this is a theta that should have a residual that is perpendicular. Hey, what's the theta that, how is that theta characterized by? That theta is characterized by the system of linear equations. Okay, exactly, there's the equations. And then we said, why is that theta the best? That's because any other theta that you can have, which is like, let's say theta hat plus z, that's going to have a higher residual value. Okay, so how do we get this theta hat there? Therefore, this candidate theta is the best one. So how do we get it? What is the formula? We had the system of equations. You can always take the thing that was multiplying with theta hat, take its inverse if possible, times the right hand side. Okay, so we have a formula here where we are representing the parameters that we want the best parameters that we can get according to corresponding to the loss function, corresponding to the 2 norm square minimization of the residuals. That theta hat is nothing but solved by a system of equations. Okay, so you can just solve it using A inverse B, basically, where A is this X transpose X and B is this X transpose Y. Okay. So any questions here? Okay, so if we step back for a second, we started with a linear model template, or what is specification. We said, hey, square loss is a good criteria to say which theta is better or not. And then we took one direction, which is using gradient descent ideas to compute best theta. Go down the ball, you get the best theta. Now the squared loss is the same as sum of squares of the residuals, okay, 2 norm square of the residuals. Okay. If you take the residuals perspective, there is a candidate theta, which is exactly shown in this slide. Okay, that theta is written as some matrix vector multiplication here, right? That's the theta. Okay, that theta is also the best theta. So either you can do gradient descent computationally to find the best theta, or you can, given the data set, which is the right hand side is all related data, right? Feature matrix and the output values of the training data, you can directly compute the best theta of the linear model. Okay, so you don't have to do gradient descent to get to the best theta. Okay, so that now what we're seeing is like two procedures to get to the best model according to the training data. Okay, and the same kind of expression also holds if you do ridge regression, for example. Yeah. So there is a question. So if there's anything other than the best theta for which the residual is perpendicular, the residual obtained is always greater as an extra positive. Yes, so that's exactly what's going on here. So if there is any other theta, so see, yeah, any other theta, then that any other theta is kind of represented using theta hat plus z. Okay, and so that theta will have a residual that is this, which is going to be the residual of the theta hat itself, which was perpendicular, which corresponded to the perpendicular residual, plus an extra term. Okay, that extra term is always positive, and so you're always going to be worse off if you pick a theta for which the residual is not perpendicular. So there's a little bit of language here. But if you understand intuition, you'll be able to not, you don't have to use all this mathematical notation here, but you should be able to say, hey, if you're not perpendicular, if your residual is not perpendicular, then your residual kind of length or magnitude is going to be longer. Okay, that's kind of intuitive, right? If you're not exactly vertical, if you're vertical, you'll have the shortest length. If you are not vertical, then you'll have kind of longer vector. So there's a question, which is that using the gradient descent procedure or using the analytical formula for ordinary least squares should yield the same theta value. Yes, that is true. It should yield the same theta value, but the gradient descent procedure has this convergence criteria. So it may be almost close to the same theta value, but may not be exactly the same. Okay, because you'll be iterating, and at some point you'll stop where you say, hey, the new theta is not too different from the old theta. If that tolerance, like if new theta and old theta are slightly different by a small value, you may still stop, and so it may not exactly be the same as the theta hat here. But in theory, they should be the same. But in practice, when you do the gradient descent, there may be a slight difference, like up to some numerical accuracy, basically. Okay. So in this slide, we're just saying that the solution, that's like the problem is solving this. Although we have formula, this formula may sometimes because there's an inverse operation here, which also you can subvert, in some ways, but may make the computation of theta, not very stable. Okay, so if you have done any linear algebra, at least computationally, you know that if the matrix is not a good matrix, the inverse sometimes may not exist, and the matrix could be singular, close to singular. There are all sorts of issues that can happen. And so they will manifest directly if you kind of try to use this formula. They will also, of course, influence how well the gradient descent procedure also works. But here, it's a little bit more direct. And so there's always a need to think through like how you want to solve for the best parameters. Okay. I don't want to spend much time on these optional topics. In the slide deck, there is some discussion on what is called QR factorization and using some decomposition ideas to estimate, to kind of discuss more on like how do you get to this analytical formula. But this is the starting point, after which you can figure out, hey, if there's some issues with the X matrix, or if this inverse is not easy to compute, then how do you deal with it? Okay. We will not do that. Okay, so we'll not do that, which means so we're gonna step to the next slide deck. There we will which is lecture 03A. Okay, so for those of you, so in 03A, we're gonna skip the first 30 slides. Okay, not so we're not really skipping like a lot of slides, but what's going on is we so can you see my lecture slide 03A? So I'm on page 31. So I'll come back to here in a second. So what's going on in this deck is so this slide that you see, page 26 in the slide deck, which is 03A, is the same as what we covered. Okay, so 02B, the end of the slide deck, kind of corresponds to 03A's slide number 26. So before that, it's all the same, the discussion about normality and all that. Okay, so so if you go to up to slide 26, there are 5 more slides which talk about some additional discussion about how do you work with this, how do you compute using the formula theta hat, and what are some nuances related to it. So it's just computational nuances related to it. Okay, so we'll skip that discussion. Okay, so here it talks about Cholesky factorization and QR factorization as ideas of first how you decompose your data matrix or the feature matrix, and then compute theta. And so we will skip those 5 slides, okay, and directly come to slide 31. So just to recap, I'm going from slide 25 directly to 31 on slide deck 03A. Okay. Let me now make this full screen. Okay. So what we've done is now let's come back to our choice of the cost function. So we defined the linear model for which we defined the loss function, square loss, for which we saw now 2 procedures, one computational using gradient descent, the other one using a formula to get to the best theta, okay, or theta hat. Okay, so those 2 were computational aspects that we saw, how to get to the best estimate. Now let's talk about why the choice of that loss function. Can we pick something else? Okay, there are of course other loss functions that we can also use to measure the difference between how well H theta predicts the output versus what the output is, right? So in particular, square difference between my prediction and the truth in the training data is not the only choice. For example, I think last time we discussed, hey, we can also use an absolute value, or we can use the difference to the power 4, for example, right? So there are many choices. But least square, so the least square objective, which is the square loss objective, is also natural. So by the way, least squares corresponds to the objective function having that square expression, the square term for each loss, for example. And least squares just means you're minimizing the squared objective. Okay. So least square was the natural choice because we discussed this when we talked about this expression also, is because it computes the distance between my prediction and the ground truth, yi versus H theta of xi, without regard to the sign. Okay, hey, whether H theta of xi is greater than yi or less than yi, I can still, as long if they're too far away, then that's not a good model. Okay, so that's what it's doing, and so in that sense, it's natural. And so if that's the case, why not use something else, right? So which is like H theta of x, which is like theta transpose xi minus yi the whole to the power 4. Okay, that's the choice that I also mentioned earlier. Why not do something like this? We can certainly use this choice of j theta, the cost function, which is shown in the red point here. But there is a nice probabilistic interpretation for the choice that we made last lecture or earlier this lecture. Okay, so let's talk about that probabilistic interpretation. Okay. So probabilistic interpretation, by the way, so far I would say that the previous lecture was focused a little bit more on linear algebra, including up to this point was more focused on linear algebra and also computation, right? Now we're gonna switch some gears and take a statistical or sorry, probabilistic perspective. So there's a question, which is why is this to the power 4? So to the power 4 and to the power 2, they all behave similarly. So this red point was just saying, hey, if all you care about is that if h theta is too far away from yi, you just want to penalize that that choice of theta, then why only stick with squares, right? Why can't you do to the power 4 or to the power 6 or any even power, right? I mean, you need even powers if you need to ignore the sign. Okay, the moment you take odd powers, like to the power 3 or without a power, then you know that if h theta is greater than yi, it will be positive. If h theta is smaller than yi, it will be negative. So we don't want loss function to kind of go below 0, for example. Okay, so to the power 4 is just a candidate. And a question exactly is what you're asking. What you may be asking next is that why not use this j theta? Okay, and now in the next few slides, we're just going to justify further why the squared loss function is also, it has an extra interpretation that makes it kind of interesting. Okay, it has an extra interpretation. That's all. But you can always computationally, if you really prefer, you can certainly use the power 4 or power 6. Okay. So this is the probabilistic interpretation, is the following. So now we are now making things random variables. Okay. So we're gonna assume, so this is an assumption, is that yi is equal to theta transpose xi. Okay, theta transpose xi is exactly our h theta, plus there is a addition of a number, this epsilon. Okay, so this number, which looks like a e or inverted 3, is epsilon, again a Greek symbol, epsilon I. Okay, so epsilon I. So we are saying yi is equal to theta transpose xi plus epsilon I. So we are actually saying it's equality. Okay, in the sense that, hey, if you have a theta, first multiply theta with xi, your feature vector, you get some number, add epsilon I. Okay, that's some extra number that you're getting, and that sum together is exactly equal to yi. Okay, so that's the assumption we're making. So what is this extra number epsilon I? It is basically an error term. It's basically the residual that we were seeing earlier. It's an error term that is not modeled by your features. Okay, that's an error term because that's something which is not which is not theta, which is not x's. So it's something which is not modeled. Okay, colloquially you can call it an uncertainty or a noise term. Okay, so what is the probabilistic interpretation? Is this. Okay, the assumption is that, first of all, we're making an assumption that yi is equal to theta transpose xi plus epsilon I, where epsilon I, we're going to make an assumption, is actually a standard normal. It's not standard normal. It's a normal distribution with 0 mean and some variance sigma square. Okay, so this notation here, again, is a short form. You don't have to write it this way. You can use just the English sentences for this. The assumption is that epsilon I is normally distributed. Normally distributed Gaussian distribution is the same thing. So it's normally distributed, and normal distributions generally have 2 parameters. Okay, and since epsilon is a number, it's a scalar quantity, we're talking about a univariate distribution. So it's only a distribution in 1 dimension. Okay, so this normal distribution has 2 parameters. Okay, 2 parameters that define the distribution, the density function, for example. So the first parameter is the mean value, which is either 0 or some number. And the second parameter is the variance. Okay, so the variance here is represented as sigma square. That's because sigma, for many of you who have done 570 other courses, sigma is the standard deviation. This is just another Greek symbol used to typically denote the standard deviation. Okay, so sigma square is the variance. So assumption is that epsilon I is normally distributed. Now epsilon I is for the ith example. What about epsilon 1, or epsilon 2, epsilon 3, epsilon 4? The assumption is that all of these epsilon 1, 2, 3, 4, whatever, 100, they're all normally distributed with the same mean and the same standard deviation. It's the same variance. And so these are called independent and identically distributed samples. Okay, so IID just means these epsilons are independent of each other and they are identically distributed. Why are they identically distributed? Because each epsilon is exactly zero mean and has the same variance. Okay, so that's the assumption we're making. Okay, this is an extra. So now what we're trying to say is, remember, if you step back, we're trying to justify why least squares is a good choice. We already knew least squares is a good choice because, hey, if the difference doesn't matter if it's positive or negative, if the difference is far, you're kind of penalizing it. So we are adding one extra perspective, which kind of further supports why least squares may be a good choice. The perspective is that, hey, if you think that the data was generated this way, that there was some unknown theta and it got multiplied with x's with like an inner product, and then this Gaussian noise, this Gaussian or normal distributed noise was added to it, and that's how I produce the output values, okay, in my training data. If that's my assumption, and within that, of course, these epsilons are normally distributed with mean zero and some fixed constant variance. Okay, it's fixed, unknown potentially. This unknown variance sigma square. This is the additional assumption I'm making. Then I can actually get to almost the same square loss objective. Okay, that's where we're getting to, okay, in the next 2 minutes or so. So then let's come back to epsilons. Epsilons are normally distributed. So we know what the expression for the probability of epsilon, the random variables taking specific values is, right? So the epsilon taking a specific value is just 1 by square root 2 pi sigma, which is the standard deviation, times e to the power minus epsilons have zero mean. So there is no minus mean here. Divided by 2 sigma squared. So this is just a standard formula that you can pick up from textbook, so you don't have to remember it. Okay, it's not important to remember the exact form here, except for some. You can see that there's some square here, and we'll pick up that part of the expression soon. So we know that epsilons follow this. The density function follows this expression, but we know that epsilon is related to y's and x's this way. Okay, so if I take epsilon is nothing but yi minus theta transpose xi, because it's an equality, right? Either I can write y is equal to something plus the epsilon term, or I can separate out epsilon and say, hey, y minus this thing is equal to epsilon, right? I can do that as well. So because I can do that, I can actually also write a distribution or a density function for yi's. Okay, so let me rephrase that a little bit. If you look at this equality, so theta, we're going to assume that theta is some unknown fixed quantity. Xi is already, it's the feature vector, so we're not going to assume anything about it being a random variable. So for now, it's also fixed quantity. Okay, so this is there's nothing to do with randomness. There's nothing to do with randomness in the sense that there's not random variables. Epsilon is a random variable, okay, which we just discussed now. So epsilon is a random variable. This is some fixed quantity. Then y is also a random variable. Okay, so a function of a random variable is a random variable. So y is a random variable, right? So if it's a random variable, it will have its own density function. So p of y. So we can write its density function. So what is the p? So we can ask, hey, what is this? What is the density function of this derived random variable? What is the probability of yi? Given everything else that specifies that random variable, which we're going to assume it's not random. Okay, so given theta and x's. Okay, so given thetas and x's, what is the distribution of this random variable? Okay, of course, if I also tell you epsilon, then there's no randomness, right? So if I tell you theta, x, and epsilon, then this is y is not a random variable. It's just a y exactly equals theta transpose x plus epsilon, right? So I cannot, I cannot say everything. So if I given theta and x, y is a random variable, which is a function of this random variable epsilon. Okay, so we can write the density of y given information. And there's a particular way that's written here. I'm going to comment on it later. So probability of y, we know it should be, if you see here, y is exactly equal to epsilon except for some offset. Okay, so this theta transpose x is just some number, right? It says it's some scalar value. Except for that, there's no big difference between y and epsilon. Okay, so if epsilon is normal with zero mean, you can easily eyeball that y is a normal distribution with a slightly different mean. Okay, if because those are not random, there's some, like, so let's say some number 10. Okay, so then y is has mean 10 if epsilon is mean 0. Okay, so you can see that the epsilon's distribution is this, which means that y's distribution is exactly the same as epsilon's distribution, except for y has a different mean. Okay, so y is also normally distributed with the mean of theta transpose xi, and variance being exactly the same as epsilon's variance. Okay, so so this is a distribution for y, and the reason I defined the distribution of y is now we're going to talk about the likelihood of the observed data, and then get to again the least squares objective. Okay, justifying why least squares is a natural choice. So any confusion regarding what we did in this slide? It's an intermediate point. If you want, I can finish the story and then we can come back to any questions. Okay, so let's actually pause here for till 4:45. And then come back to kind of working through this, and we'll start with the simpler examples and talk about likelihood and so on. So let's pause here and resume at 4:45. Okay. So what I'm going to do is, the context is we want to support why least squares or just the squared loss objective is a good choice, especially working with linear models. And so we started looking at a probabilistic interpretation. And this slide was encompassing that, hey, if we assume that y's are produced using thetas and x's with some additive noise, which we assume to be Gaussian with zero mean and constant variance, then we can get a distribution over y's. And then what we're going to do is try to define that theta, which maximizes likelihood of the data. Okay, and so we'll get there. But before that, for our problem, but before that, I want to talk about a more basic setting, which is the probability of data, okay, and general probability of events. Okay, so remember, so events map random variables map events to some values like 0 and 1. And probabilities are assigned to events. Okay, so events in a sample, events from a sample space, right? So you have this event. Let's say this is the coin flipping event, and so we have 3 heads and 7 tails. Okay, so there were 10. We flipped a coin 10 times, and it landed heads twice and tails 7 times. Okay. So if we know that the coin is unbiased, as in like, hey, the probability of having heads is the same as probability of tails, then the probability of this particular event happening, which is heads in the first trial, heads in the second trial, heads in the third trial, tails in the fourth trial, and so on, that is equal to 0.5 times 0.5 times 0.5 times 0.5 all the way 10 times. Okay, so that's why there's a to the power 10. And why is it a product of these individual coin flipping probabilities? Is because we're going to assume that each, we'll typically assume that each outcome is independent of the other outcome. Okay, so each realization of heads, the realization of heads in the first coin flip has nothing to do with the realization of heads in the second coin flip. Okay, so that's why it's 0.5 to the power 10. Okay, and so let's not digress to this question, because we have the we want to kind of motivate likelihood and maximize the likelihood. So even if you have a biased coin, so if you kind of if you flip a coin 10 times, you may see 3 heads and 7 tails, but if you flip a coin 100 times, you should ideally see a 50%, 50, close to 50 of them should be heads and close to 50 of them should be tails. Okay. So if you flip a coin a lot of times, then ideally, if the coin is unbiased, then you should see an equal proportion of the two outcomes. Okay. So if you see very skewed proportion of one of the outcomes versus the other, then you probably your coin is unbiased. Okay. But let's come back to the question, which is, let's say we don't know the bias of the coin. Okay, so which is the unknown parameter that we want to estimate. Okay, so this is a completely different estimation problem from linear regression that we have been discussing so far. But let's think about it as well. So this is a purely, here's a coin. I don't know its bias, or I don't know with what probability it will land heads. But I give you this experiment data, which is I have tried 10 different times to flip this coin, and 3 of the times it landed heads, and 4 of the times 3 of the times it landed head, and 7 of the times it landed tails. Okay, so we start with some assumption. We don't know what the actual bias is. Let's say probability of head is equal to theta, which means that probability of tail is equal to 1 minus theta. Those are the only 2 outcomes possible, let's say. And let's say each coin flip is independent as well. We observed some we observed some events, in particular the event, which is that the first 3 trials, so Y1 to 3, okay, this is just a shorthand again, is just exactly what's written in this slide. The first 3 outcomes are heads, and the next 7 outcomes are tail. Okay, so that's this data set D. Okay, now I'm reusing the word data set D here because it actually has a very similar use to the way we're using capital D for our feature comma output data set, those pairs X comma Y pairs. So this is our data set D. The size of the data set, this is generally a shorthand again to say how big is this data set. These 2 perpendicular vertical lines is the size of the set, okay, which is equal to 10 here. Now, what we want to answer is, hey, I don't know what the bias is of the coin is, but here's the data that we observed. Given the data, tell me what is the theta that makes the most sense. Okay. In other words, what parameter theta makes my observation of these heads and these tails the most likely? Okay, so that's the question. So that's exactly the statistical question. Okay, so statistics is all about given data estimating something about the underlying probability distributions. Okay, so we want to find out what parameter theta makes the our observation of these heads and tails most likely. Okay, and the way we do it is to define, hey, for any theta, can I quantify what is the likelihood of the data that I observe for any theta? So what I want to define is a function which says, hey, if this was a theta, this is the probability with which I would have observed this data. Okay, so that's what I want to quantify. What is the likelihood of the data given as a function of theta? Okay, so likelihood of data is written as this function L of theta. So it takes theta as an input and spits out, hey, if this was the theta, this is the likelihood that you observed the data that you have. So, or you can say, hey, we can actually add explicitly the data as a second argument if you want. And the likelihood of the data given this function, given the parameter theta, is the probability of data given theta. Okay, what is the probability of data given theta? It is in our case we had 3 heads and 7 tails. We know heads happen with probability theta, and tails happen with probability 1 minus theta. So we had 3 heads. So it's theta times theta times theta. That's theta to the power 3. And tails happens 7 times. So it's 1 minus theta to the power 7. So why is there powers? Because they're products. Okay, why are they products? They are independent events. Okay, the first head has nothing to do with the second time you're getting heads or tails has nothing to do with the first time you got heads or tails. Okay. So what we define is some sort of a likelihood function. So what is it doing? Hey, you have this observed data. Every theta that I give you, you can tell me what is the likelihood of observing the data given this theta. Now we can ask, hey, if that is the case, can you find that theta that maximizes this likelihood? Okay, so can you find that theta that maximizes this likelihood? And so that in short form is written exactly the way we've been kind of looking at it for the linear situation, which is arg max instead of arg min, okay, because we want to find the theta that maximizes the function L theta. But theta we know also has to be between 0, 1. Okay, so this is this restriction that was kind of not there before when we were writing argmin cases that we saw before. Okay, so this is a likelihood maximization problem. Okay, maximizing the likelihood. A brief comment about this restriction of theta between 0, 1. So this type of restriction, I think I mentioned at the beginning of the class as well. So the gradient descent techniques that we saw earlier, gradient descent, stochastic gradient descent, mini-batch gradient descent, they don't consider this restriction. Okay, at least the versions that we saw in the slide, they don't. The ones in the slide don't consider this restriction, as in this. Hey, the theta has to be, or the parameter that you're searching for has to be between some low value and some high value, for example. Okay, if you want that restriction, there are some other additional things that you need to do, and the names of the algorithms are slightly different also. Okay, I mean they can use gradient information, but there are algorithms which use gradient information to find the best theta, but the computational procedure needs a little bit more work, because now you have a restriction that theta should not be anything below 0 or anything greater than 1, for example, in this case, right? So we have not discussed those algorithms. So for now, the techniques that we've seen are kind of, they're not restricting, you're not restricting the search space except for defining it as a function of the loss function. Okay, so just keep that in mind. So let's come back here. So this, as I said, the last equation in this slide is just a shorthand to say, hey, I want a theta that maximizes the likelihood. Okay, so because with that theta which maximizes the likelihood, the probability of this data under that theta is the highest. Okay, and I've already observed the data that kind of supports that. Hey, you observe this data. What is the most likely theta that supports that observation? Right. So it's an equivalent way to say this. So that leads us to a procedure. It's not a procedure; it's just a formulation. The defining the problem for which you can use whatever computational procedures to solve it. The problem is called maximum likelihood estimation. Okay, this is the estimation problem for estimating the parameters, like in the previous example. This is a different problem than estimating the parameters of a linear model. We'll come back to the estimation of linear models. Linear model, we have already saw several computational procedures, right? Gradient descent based ones, as well as the analytical formula. Here it's a different problem, but still it's a kind of a search problem, right? So you can see that when I wrote this last equation here, it is a search problem. There's a different objective. It's not a loss function, but some other function. I'm maximizing instead of minimizing, and I'm also searching over some parameter theta. Okay, we're reusing the word theta here, but it's clear, right? So theta is just the probability of head, which is some number between 0 to 1. So the maximum likelihood estimation problem is basically exactly that. What makes your observations most likely? Okay. Now we'll come back. Now we'll switch back to this situation here. So we saw that the likelihood of our data, which is yi's, yi's and xi's are our data. Okay, but yi's are the only random variable, so we can only ascribe probabilities to random variables. So we'll talk about what is the probability of observing these outcomes, these output values, given, let's say, features and theta. Okay, so given features and theta, you observe there's some likelihood of observing these yi's. Okay, now can you tell me which theta maximizes the likelihood of observing the yi's that you already observed? Okay, so that's the maximum likelihood problem. So let's come back here. So the likelihood in our case, okay, so now we're tying it back to the regression setting. So likelihood in our case is the thetas are unknown fixed parameters. We want to find out. So theta is not. So theta is the unknown fixed parameter. It's basically the mean of the random variable yi, right? So sorry, it's not the mean itself, but it parameterizes the mean of the random variable yi, for example. So we saw that here, right? So probability of yi given parameter theta is that if you tell me theta, I can tell you what the mean of this random variable is. Given the mean of the random variable, observing a specific yi is yi minus the mean, the whole square, divided by 2 sigma square. So this is just this expression with the very crazy looking coefficient and exponent. This is just a definition of the Gaussian distribution. We saw it like 2 slides right before the break, right? So likelihood of the data given theta is just the product of each example. I is equal to 1 to m. Let's say there are 100 examples, and it's a product of 100 terms of probability of yi given xi comma theta, right? Given xi and theta, right? So this probability of yi we just showed right before the break that is exactly equal to the Gaussian distribution with a certain mean, with a mean different from 0. Okay, epsilons are 0 mean, and so yi's are not 0 mean. Yi's have a mean which is theta transpose xi, right? So this is the likelihood of data, right? Likelihood of the data, and if theta given any theta. Okay, now we want to find out which theta is the one which maximizes the likelihood. Okay, let's can try to maximize the likelihood with respect to theta. Hey, you observe this data xi y pairs, which is our data set D. Can you tell me which theta maximizes the likelihood of the data? Okay, so the data, the probabilistic part is just yi, but what is the theta that maximizes this the likelihood of this seeing these yi's that we saw? Okay, so that means we want to maximize L theta. Okay, so maximizing this expression seems unwieldy. So let's actually take it one step at a time. The way we're going to maximize it is we'll maximize log of L theta. Okay, instead of maximizing L theta, we will try to maximize the log of L theta. Okay, why is that the right thing to do? Is remember, so we are trying to figure out theta that maximizes likelihood, just this theta. So if you think of the sigma and 1 by square root 2 pi, they're not, they don't change if you change theta, right? So there's just some multiplication coefficient. You might as well think of this as some constant. Okay, so you can ignore this coefficient here as well as this sigma here. Okay, it doesn't matter what the sigma is. Okay, so or you can keep the sigma. All I'm saying is that this is just a multiplication coefficient. It's some constant. It doesn't depend on theta. So you can ignore it for optimization, because maximizing 10 times j of theta is the same as, maximizing 10 times L of theta is the same as maximizing L of theta. The 10 doesn't make any difference. So a bunch of such products, you can drop them. Okay. Now, L of theta then is basically a product of exponents. Okay, it's product of exponents. So product of exponents just means that it's e to the power a bunch of additive terms. Okay, so log of, so it's e to the power x times e to the power y, or let me not use x and y, but e to the power a times e to the power b is equal to e to the power a plus b. Okay, so it's just if you multiply 2x e to the power somethings, then it's just equal to e to the power addition of the exponents. Okay. That's a simple fact. So basically our likelihood essentially boils down to e to the power some terms in the exponent. Okay, so so instead of maximizing the likelihood, we can actually maximize log likelihood, and will not change the solution. Okay, and we'll talk about this maybe again. So let's try to maximize the log of the likelihood. Okay. Sorry, instead of talking about it later, let's talk about it right now. So why we can do this is exactly because there's a claim that we can maximizing L theta. The thing that maximizes L theta is the same thing as in like the theta that maximizes L theta is the same theta that also maximizes log of L theta. Okay. Why is that? We need to justify, but let's come back to that later. Okay, so it is an interesting property. But we'll talk about it later. Okay, so I just want to not digress again. So let's hold on to this for a second. So let's maximize log of L theta. So what is log of L theta? Let's call it script L. Okay, so this little L or script L is just kind of trying to show that, hey, it's different from the likelihood function itself. Okay, so the script L is a log of this thing in the expression, right? Just product of bunch of exponents, which I just said is if there's a log of log of products is the same as sum of the logs. So log of a times b is equal to log of a plus log of b. Okay, so there's sum of that, and you can ignore this coefficient, or you can keep it, but it doesn't depend on theta. But in this equation, we're just keeping it. And then log of exponent, log and exponent cancel each other out. So you have this remaining term. Okay, so log and exponent canceled in the second term. The first term just involves a log, but that anyway doesn't involve theta, so you can ignore it. But here we have not ignored it because we want equality. So let's come back to what the point we want to make. So let's say maximizing L theta is the same as maximizing log of L theta, log likelihood. Now log likelihood is exactly this term, which is on the which I'm hovering, which I'm using my cursor over. Okay, so this expression, you can see that maximizing the likelihood. So there's not, the first term has nothing to do with theta, so you can ignore that. Maximizing the negative, again, this is nothing to do with theta, so the coefficient here 1/2 sigma square, you can ignore it. Maximizing the negative of sum of squares. Okay, maximizing the negative of sum of squares is the same as minimizing the sum of squares themselves, which is this. Okay, so the sum of squares is this, sum of I is equal to 1 to m yi minus x theta xi the whole square, right? So all this effort is to show you that if you take the probabilistic perspective, which is make the assumption of Gaussian distributed error terms or residual terms with zero mean and constant variance, then maximizing the likelihood of the data and define the maximum likelihood estimation problem is exactly the same as minimizing the least squares objective. Okay, so maximizing the log likelihood, is the same as minimizing the least squares objective. Okay, now why is log likelihood, maximizing log likelihood the same as maximizing the likelihood? That's because the log function is a increasing function. Okay, a log function, if you plotted log as log of, let's say, x or log of a, when a is small, so when a is so first of all, log of a is defined in the positive region. Okay, so it has to be, you have to, the minimum value is 0, maximum value is infinity. When log of a, so when a is close to 0, log of a is smaller, potentially negative infinity. And when a is large, log of a is also increasing. So log of a always kind of increases. Of course, it doesn't increase linearly. It's some curve like this, grows sublinearly, but it's an increasing function. And so if the function is increasing, then applying that function to the objective function doesn't change the solution of that optimization problem. Okay, so it doesn't change. So let's come back here. So if you apply a log function on the original objective, since log is always an increasing function, wherever the original function was getting a maximum, the other function, the new function with the log, also gets a maximum. Okay, so let's come back to this. So the key point is that from the probabilistic perspective, the squared loss is well supported, because if you make these normal distribution assumptions of how the data got generated, it tells you that the right thing you want to optimize for is actually the squared loss, because you're maximizing the likelihood of the data under a probabilistic model is the same as minimizing the squared loss. Okay, so any questions here? Okay. So that's the, an important observation, which is new. So in the overall context, we start with the linear models, squared loss, then we define gradient descent procedures, then we talked about normal equations, then we said, hey, let's now add an extra perspective, which is a probabilistic perspective. Under the probabilistic perspective, if you maximize the likelihood of the data under a specific model, which is this Gaussian this normal distributed error terms and with zero mean and constant variance, then in the probabilistic perspective, maximizing likelihood estimation, maximizing the likelihood is also the same as minimizing the squared loss. Okay, so if you want to minimize, and if it's the same, then we can exactly use the procedure that we have discussed before. We can use gradient descent or the normal equations to get theta hat. Okay, so the computation procedure remains the same. What we've added is just an extra interpretation of why squared loss is a good candidate. Okay, why not to the power 4 or why not to the power 6? Well, squared loss at least has an extra interpretation, which is this probabilistic interpretation. Yeah, so I guess this is exactly what I said. Yeah, but we added this probabilistic interpretation, but we can do, of course, we can do least mean squares or OLS or least mean squares. I'm using the terms OLS. OLS just stands for ordinary least squares, and least mean squares is just the objective function. Okay, mean square function is the function that we saw as, difference between prediction and output, the whole square. So although we added this probabilistic interpretation, even without this interpretation, we were anyway saying that the loss function has some nice properties, and let's just minimize that loss function, right? So you don't need to have this probabilistic interpretation to solve for the best linear model. I mean, because the best linear model is defined exactly according to the loss function. You can directly prescribe what loss function you want to use, but square loss just happens to have an extra interpretation that supports it. Okay, and of course it makes some assumptions, but which of course are I guess have a pro and a con. Pro is that they give you extra interpretation, but con is that maybe the data is not corresponding to this probabilistic model. Okay, data may not correspond to this probabilistic model. Okay. Yeah, and a couple of points is that we don't need to know sigma square, and that's why I was saying we can ignore sigma. And even if you don't know the variance, we can still do linear regression, right? And in fact, we did that before the probabilistic interpretation. Even for probabilistic interpretation, we don't need sigma square. Yeah. So any questions here? Okay, I am going to switch over to slide 03B. Okay, if you're not seeing slide 03B, which has 89 slides here, then just let me know. But let's see, I'll make it full screen. Okay, so what we're going to do we have spent quite a bit of time on linear models. Now, what we're going to do is, now that we've been introduced to the idea of maximum likelihood estimation, we will now try to use linear models. So far when we've talked about linear models, we've kind of were focusing on regression, actually. We'll try to now talk about classification as well. Okay, and so we'll try to now look at extensions to this linear model idea that can, make it applicable to beyond regression, for example, classification setting, as well as some other extensions. Okay, so let's actually talk about first classification. So we want to use a linear model, but we don't want to do just regression, but we want to also do classification. So which means if you look at this illustrative plot, remember if we were doing given homework and exam scores, so homework and exam values, two features, we want to predict score. Score was a number between, let's say, 0 to 100, and so we were able to create a linear model, which was this like a dashed line here that you see in this illustration, right? Now, what if we instead want to not predict the score, which is that number between 0 to 100, but instead grade? Okay, and this is something that we saw when we talked about KNN before. Let's come back to this illustrative data set. Okay, so now we have homework and exams, two features, but instead of predicting the number, we're going to predict predict a class. Okay, pass or fail. So let's say there are two classes. So red is one class and blue is another class, and we want to say, hey, what is the class of this new data point. I mean, build a model, hopefully based on this linear model idea, such that any given new class, like the black dot here, what is the ANS grade, right? So we'll start with the simplest case, which is this binary classification that we saw in the previous illustration slide. So which is to have two cases. So the output y only takes two values, class A versus class B. And in fact, we will say, hey, class A is 0 and class B is 1. Okay, so we're going to give them explicit numbers. Okay, let's say one of the class is, let's say class 0 is called a negative class, and class 1 is a positive class. Okay, so if in binary classification, people will refer to one of the classes being negative and another classes being positive. It's just because of historical reasons. It's not that one class has some negative connotation or one is positive connotation. It could have, but they're just two classes, and typically you would refer to one of them as negative and one of them as positive. Okay. Now, this is different from regression problem that we saw earlier, where we were predicting scores. Okay, although y is, instead of all possible numbers, it's not on the real line output. It's taking the set of output. The output space actually is the set which has only values 0 and 1. It's a restriction of the output. It's not, but it's beyond that. Okay? It's different from regression problem. For example, one quick point is that this negative class and positive class may not have an order relationship between them. Okay, so that, for example, a 0, the order relationship just means that 0 is it less than 1, is negative class less than positive. There's no such connotation. Okay, so that's a big difference. But let's actually we'll talk about that difference again. But let's talk about a slightly different illustration. So I mean, some motivation. So here's a binary classification example. So spam versus not spam. Okay, so we're not talking about spam, which is a food ingredient. We're talking about spam, let's say email classification, which many of the popular email vendors do. So, or we can do other motivation example is object detection, where you can classify what is the object in the image. Okay, so the image is somehow the raw data from which you can create potentially a feature vector. So that image is, essentially becomes a feature vector. And given that feature vector, you wanna, let's say you're doing binary classification, then your class is either there's a cat or there's not a cat. Okay, so one of the classes is positive class, one of the classes is negative class. Okay, that's called object detection. Okay, sorry, object detection. I mean, so we're not using these terms very formally, but there's an object detection problem. Or object classification problem. So in real life, there are many applications which are classification related. We've already talked about classification in Canaan, so I will not spend too much time on these examples. But there's a lot of applications to predicting whether review is not, is fraudulent, or whether it's true review, whether somebody is being fraudulent, and so on. So there are many applications of such binary classification. And sometimes classification is not always that obvious. So for example, we may need a continuous value instead of a class 0 versus class 1. Okay, and now once we have a continuous value, it seems like a regression problem, right? So classification is not always obvious. So let's talk about a connection which connects two classification, right? Like saying class A versus class B. But instead of producing an output which directly says, hey, class A versus class B, we're going to produce a continuous value between 0 and 1. And using that continuous value, we can eventually say, hey, if the continuous value, which is between 0 and 1, which is in the range, it could be 0.01, 0.1, 0.3, 0.7, 0.99, 1. So we build a model which produces a number continuously between 0 to 1. And then if the number is close to 0, we can say, hey, it's probably class, negative class. And maybe if the number is close to 1, maybe we'll say positive class. So we can use continuous values to deal with classification. Okay. So And the linear model example for doing this is called logistic regression. Okay, so let's look at linear models. So here's a different data set. I think earlier in the previous slide, we were looking at the auto data set. Here we're looking at Boston housing data set. Here's a plot of median house value on the y-axis versus percent of households with a low socio-economic status. Okay, so some numeric value that's available as a column in that data set. And the red line shows a linear fit. Okay, so linear fit may or may not be the best here, but you can see that it was a pretty decent relationship between house value versus percent of households with low socioeconomic status in a location, in a region. So we're gonna build on linear model idea, the model specification, to change it so that it can work with it can work to produce a continuous value between 0 to 1 instead of producing a value between minus infinity to infinity, which is what typically a regression, which is what h theta of x was doing before in linear regression. We're going to try to compress the output to between 0 and 1. Okay, so how we're going to do that is the subject for the next few minutes. Okay, so first question is that, can we just use linear regression? Why do we even have to do anything more? And the answer is yes, we have to do something more, because if we don't explicitly ensure that the output of the linear regression model is between 0 to 1, it can easily produce a number which is greater than 1 or less than 0. Okay, so because there's no other control, right? So if I pass an input which is producing a value 0.99, if I add some extra values to the input, maybe it produces a value 1.01, and 1.01 is not desirable, okay? Because we want to get values between 0 and 1. That's our preference. So actually, there's a question which I just saw. Are we going to use linear models for classification here? Yes, we are trying to use linear models for classification. And logistic regression that you saw the phrase a slide ago is exactly an example of using linear models to do classification. Okay. So logistic regression is just there's the word regression in there and the word logistic there, and you'll see how just linear regression is being massaged into doing a classification here. Okay, but you can actually use linear regression potentially directly also to predict class 0 versus class 1. Maybe we'll talk about it at the end. Okay. Although here it says the prediction will go out of bounds, but you can always say, hey, if the value is greater than 0.5, let's say it's class 1. If the value is less than 0.5, let's say it's class 0. So you don't even have to do more, right? So let's say you just know linear regression. You have a classification setting. You can just say, hey, if I'll just do linear regression, produce an output. If the output is greater than 0.5, I'll just say it's class, positive class. And if it's less than 0.5, let's say it's negative class, for example, some threshold. But to do that, you do need data where the output is actually numeric, right? So if you saw the data, that illustrative data that I showed you a few slides ago, that data had homework, exam, but it only had grade. Okay? It did not have the scores. If you don't have the scores, you can't build a linear regression model. But if you have the scores, then certainly you can build a linear regression model and maybe pick a threshold. Hey, if it's greater than, the score is greater than something, let's say it's pass. If the score is less than something, you can say it's if it's fail. Okay, you could do that. Okay. Now, but here in this slide, we're asking the question whether can we use linear regression for predicting 0, 1. The answer, which is that not directly, right? So you have to deal with the fact, somehow with the fact that the predictions could go out of bounds. And I said, hey, if you could ignore bounds and just say, hey, if large number, one of the class, low number, the other class. Okay, that works for binary classification. So there's actually a question: logistic regression is better for predicting 0, 1. Yes, because logistic regression is something that's going to go beyond what I just said, which is linear regression. If you want to use it for classification, as long as you have training data which had the scores, you can always threshold whatever is predicted to be above or below, and then just say class 1 versus class 0. But logistic regression directly works with the thresholded data. So you have features and not scores, but actually pass or fail, for example, in our illustrative setting, and still build a linear model. And that linear model is going to produce numbers between 0 and 1. Okay. they'll produce numbers exactly between 0 and 1, so they're not going to go out of bounds. And then given that number, let's say it's the logistic regression, for example, produces a value 0.1, you can just say, hey, 0.1 is close to 0, let's say class 0. So you can still do the same. It's just that it's going to work with the actual class labels to build a linear model. Okay. So I hope I didn't confuse and step too many steps ahead. But so we're going to linear model can be used, but it has this issue. Okay, so I guess that's the summary here. But we're going to fix that using logistic regression. So we just want to ensure that, hey, linear regression is already producing numbers between -infinity and infinity. Can we somehow shrink those numbers to 0, 1? And we'll also deal with the fact that the training data is slightly different now. Instead of scores, we have pass fail, but we'll fix that in a second. Right now, we'll say we want to say that, hey, output, if it's going from -infinity to infinity, which is what linear regression typically will do for a single valued output, can we compress it to 0, 1? Okay, and the answer is yes, we can actually do that. So let's say, yes, somebody said something.
I have a question.
Yeah.
Okay, so I could be wrong. I could be wrong with my interpretation, but isn't logistic regression derived from the general equation of linear regression? I mean, given the fact that it is a continuous variable, then we convert it to more of a step function, which then in turn becomes a sigmoid function. So, I mean, for logistic regression, we are just taking into consideration the threshold or like the probability of what the classification could be, but for linear regression, obviously the output could be, any given thing between 0 and 1. Is that correct?
I think it's just, I don't exactly follow what you said, only because, it's a little, so there's a strong relation between linear regression and logistic regression, of course, and that's why we are studying it in succession. Both are linear models behind the scenes. Okay, so linear regression, there's Theta, which is a linear function of x, and here also there's going to be a linear function of x. It's just that they're going to be slightly massaged for classification versus regression. But I wouldn't say one is a general version of the other.
A derived version. I feel like I could be wrong then again, but I feel like I studied it somewhere long back, or maybe I'm remembering it wrongly, but like logistic regression can be derived from linear regression, like from the general equation of it. But
what is meant by general equation? That's I guess the confusion here.
Say for example, when you get the output in R could be like y is equal to mx plus c, and then you equate it equal to theta, and then the e to the power goes to the right hand side. So it becomes
no. So there's some mechanics behind the scenes. But so far we have not seen any general equation, right?
Okay.
So far, right? So we just said our expression was h theta. Actually, let me just see, show you. So far we've done this. Linear regression for us just means h theta of x is something like this, and given any x, it produces some real number, right? We are going to do probably what you're saying, okay? But we'll do it one step at a time. Yeah. So it's certainly related, okay? I mean, there should not be any ambiguity there. It's super related. I mean, both have linear models behind the scenes. So what's the time? Okay, we are running out of time. Let me just comment exactly what what Ikas was saying. So we have this. We start with our linear hypothesis function, okay, h theta, but it produces numbers between -infinity and infinity. How do we get a number between 0 to 1? We're going to use an additional transformation. So let's produce -infinity, some number between -infinity and infinity, and then we'll further massage it such that we eventually get a number between 0 to 1. How do we do that? Here's an example function, right? So our now new h theta, okay, not the original one, new h theta, the new function. We're going to say, hey, we're going to first do inner product just as before, but then we're going to add an extra function g. Okay, so we're going to compute theta transpose x, but then we'll have an extra function that operates on the output here, and then finally produces a number between 0 to 1. Okay, that's easy to see, right? So so here at the bottom, you can see there's a x versus y plot. Here, if you think of this g function as this red function, if I produce an input, okay, between, let's say, -infinity and infinity, like you can see this is a particular example of a g function where it's saying, hey, if it's any number between less than 0, set it to 0, any number greater than 1, set it to 1, and any number between 0 and 1, leave it as it is. Okay, that's one g function. Okay, so this g function, what is its purpose? It's just ensuring that whatever is the input, that input, irrespective of whatever the input is, output is between 0 and 1. Okay, it's like some sort of clip or thresholding going on, right? That's not exactly the function that we'll use, but this is the type of idea that we'll use to define the logistic regression model. Okay, so this function, the problem is there's some, sudden bends here which we don't like, because we like gradients, and we like gradients, and so these sudden changes are not good for. So this g function is not differentiable. Okay, so for example, g of 0 is okay. It's 0. First of all, it's not between. It's not 0.5. Okay, that's a minor point. You can shift the whole function down if you want, or sorry, to the left if you want. But the second point, which is that it is not smooth. Okay, not differentiable. Not smooth just means not differentiable. But so in that sense, we want to fix that. And so the function that we'll use, and I'm going to pick up from here next class, is that the g function that we're going to use is called a sigmoid function. Okay, so let's just do exactly what we're doing in linear regression, compute the theta transpose x. But one extra step that we'll do is apply this g function, which is 1 by 1 plus e to the power minus z. Okay, so if whatever is the input, 1 by 1 plus e to the power minus of that number. And that turns out to be a nice function which, whatever be the input, between minus infinity and infinity, just squishes the output to between 0 to 1. Okay, and so we'll kind of pick up from here next lecture. Okay, and so if you have some questions and comments, then let's stay back and discuss it. Otherwise, I'll see you guys in class next week.
Thank you so much. Thank you.
Thank you.